It began not with noise, but with a silence, the kind that follows a revelation too vast to be processed. In early July 2025, when the Atlas survey in Chile recorded a faint, fast-moving streak cutting across the stars, astronomers didn't expect it to rewrite interstellar history. Yet just weeks later, as trajectory models confirmed it wasn't from our solar system, a third name joined the shortlist that once felt mythical. After Oumuamua and Borisov, now came 3I Atlas. But this time, something changed. NASA's channels went quiet. Updates that usually pour out in coordinated bursts, orbit diagrams, spectral analyses, even informal commentary, faded into a void. The silence wasn't denial, it was deliberate withholding. Behind that hush, telescopes kept watching, recording every strange flicker and fragment the object shed as it drifted toward the sun. By late August, data from both JWST and the VLT hinted at something deeply unusual. 3I Atlas was outgassing carbon dioxide far beyond where such activity should be possible. At nearly 5 astronomical units beyond Jupiter's orbit, it was venting like a living thing, long before sunlight could melt typical cometary ice. In the astronomy community, that triggered whispers. The patterns of its brightness, the polarization of reflected light, even the odd backward-facing anti-tail that pointed toward the sun, none of it fit comfortably within comet physics as we know it. Observatories released partial data. NASA didn't comment. And that silence, it felt almost strategic, because if 3I Atlas truly behaves as the instruments suggest, then its very chemistry challenges what we thought interstellar matter could be. I remember the night when the data stream paused. The Minor Planet Center had already logged the orbit, a hyperbolic curve slicing through the solar system at roughly 37 miles per second. Too fast, too clean to be gravitationally bound. But then, as astronomers prepared to publish the first consolidated brightness curve, NASA's internal data flow froze. For several hours, the JWST's photometric logs, normally mirrored in open-access archives, vanished from the usual update cycle. It wasn't censorship. It was something subtler, a recalibration period that somehow lasted days. In that absence, theories began to multiply. Some researchers whispered about instrument saturation, others speculated about data inconsistency. Yet, when the calibration files reappeared, the object's behavior still refused to make sense. 3I Atlas brightened as it moved away from the sun, not closer, a behavior seen before only in the faint echoes of Oumuamua's rotation anomalies. Its light curve displayed rhythmic oscillations, as if pieces of the body were tumbling apart in a slow, controlled sequence. Spectroscopic analysis from the Gemini North telescope added a new layer. The coma surrounding it was rich in carbon dioxide, but nearly devoid of water vapor. That ratio, CO2 to H2O far beyond normal cometary thresholds, suggested it wasn't just an icy wanderer from another system. It was a relic of an environment fundamentally different from ours, one where volatile ices froze at far colder temperatures, where chemistry itself evolved under alien suns. Still, what truly stirred unease wasn't the chemistry. It was the polarization data. Instruments measuring how light scattered off 3I Atlas's dust detected a strong negative polarization, an optical fingerprint unlike any other object on record. To trained eyes, that meant the surface was smoother, darker, and composed of particles smaller than those in typical comets. It reflected light the way carbonized glass would, absorbing instead of scattering. And all the while, NASA said nothing beyond confirming its interstellar status. No public press briefings. No open discussion panels. Even internal coordination between research centers grew fragmented. For many scientists, that silence became louder than any press release could have been. Because this wasn't just about an object from another star, it was about a pattern forming in real time. 3 interstellar visitors in less than a decade, each stranger than the last. And with 3I Atlas approaching its closest pass to the sun by the end of October, every night's observation could either confirm our models or fracture them completely. The question no one could answer was simple. What exactly was NASA waiting for? When October arrived, the tension in the observatories became almost physical. Every night, the orbit of 3I Atlas was recalculated with obsessive precision. Its perihelion, the closest approach to the sun, was predicted for October 30th, at roughly 1.4 astronomical units. Yet, days before that point, something quietly shifted in the data. Images from the Very Large Telescope revealed an unexpected asymmetry in its coma. Instead of expanding evenly outward, the gas cloud seemed to stretch in two conflicting directions. One tail following the object's path, and another, faint but distinct, aimed toward the sun. This anti-tail phenomenon, while not entirely unprecedented, was disturbingly pronounced. It hinted that dust grains weren't merely being pushed by solar radiation, but perhaps pulled by something more intricate, an internal fragmentation, a subtle structural collapse happening from within. Then came the brightness spikes. Observers from Mauna Kea noticed fluctuations that didn't match any rotational or thermal pattern. The object's magnitude swung dramatically within hours, as though its reflective surface was altering shape mid-flight. At one point, its overall brightness increased by nearly a factor of 3 before dropping just as abruptly. This wasn't random. It felt rhythmic, almost biological in its recurrence. Behind the scenes, a few researchers at NASA's Goddard Space Flight Center tried to model the data, correlating it with what was known from Borisov's volatile emissions and Oumuamua's non-gravitational acceleration. But none of the models fit. The equations always broke under the same variable: CO2 outgassing at distances where sunlight should be too weak to cause it. The only explanation that didn't violate known physics was internal heat, yet 3I Atlas, by all infrared accounts, was cold. This contradiction struck deep. How could something so far from the sun behave like a comet, already boiling with energy? Some began to suspect that 3I Atlas was fragmenting, venting gas from newly exposed layers. Others proposed that its CO2 wasn't sublimating, but being released by electrostatic effects, dust cracking under solar wind pressure. A few more daring voices, mostly outside NASA, whispered about self-shadowing geometries, that the object's rotation was creating thermal pockets that ignited in waves. Still, the public silence continued. Even as new measurements poured in from independent observatories, NASA maintained its official restraint. "We are reviewing data integrity," one brief statement read. Nothing more. And yet, among the astronomers trading encrypted emails late at night, the real fear was spreading. What if 3I Atlas wasn't just acting strange? What if it was showing us a new kind of interstellar matter, one that defied the boundary between solid gas and time itself? By mid-October, the silence had evolved into something heavier, a waiting that bordered on reverence. Every new set of data arrived like a confession from the cosmos, but NASA's voice remained absent. Inside the community, the frustration was beginning to fracture alliances. The European Southern Observatory released partial polarimetry readings showing that 3I Atlas's negative polarization was deepening as it neared the sun, a property that, instead of stabilizing, was intensifying. The implication was unsettling. Its surface wasn't merely reflective dust, it was transforming. Infrared readings hinted at a thin crust of refractory carbon, possibly a product of ancient cosmic rays bombarding its surface over millions of years in interstellar space. As it warmed, those layers began to fracture, releasing gases trapped since before the birth of our own solar system. That alone should have been historic, a direct sample of pre-stellar chemistry. Yet no official announcement came. Some insiders began to suspect that NASA's silence wasn't rooted in secrecy, but in scientific caution. The agency had been burned before, by Oumuamua's hype, by Borisov's overinterpretations. Perhaps this time, it sought to avoid fueling a media storm before the data stabilized. But the timing was odd. Every observatory, from Subaru to JWST, was observing simultaneously, and cross-correlations demanded centralized coordination. Without NASA's leadership, interpretation risked divergence. Then, on October 22nd, a small anomaly appeared in the photometric stream. The object's brightness dipped sharply, then plateaued, as if a portion of it had sheared off. Some observatories interpreted it as a fragmentation event, a chunk breaking free under internal pressure. Others thought it was rotation-induced shading. Whatever it was, the light pattern that followed had never been seen in any cometary model. The reflected polarization inverted briefly, as though sunlight was bouncing off a surface smooth enough to act like a mirror. It was then that one internal NASA memo, later leaked to the astronomical community, revealed the agency's true dilemma. The document described uncharacterized albedo events, moments when 3I Atlas reflected light with efficiency impossible for its known composition. It wasn't glowing, it was flashing, in precise alignment with its rotational period. That detail, more than any chemical oddity, rattled scientists the most. Because if those flashes weren't artifacts, If they were truly real, then 3I Atlas wasn't just changing under solar heat. It was responding to it. And the question whispered across observatories that week was one NASA dared not speak aloud. Could interstellar objects carry a form of material reactivity we've never encountered, something that wakes under light? The night before perihelion, the entire world watched the sky, waiting for something to break or to speak. The morning of October 30th came with a strange calm. Around the world, telescopes pivoted toward the sun's eastern limb, where 3I Atlas was now threading its closest arc, a luminous speck only a few degrees above the dawn. For months, we had chased data in fragments, decoding patterns that refused to hold still. But that morning, the sky itself seemed to tremble with anticipation. From the Las Campanas Observatory, the first spectral readouts arrived before sunrise. They revealed an unexpected chemical signature, a spike of cyanide emission, faint but clear. CN radicals, glowing faintly blue in the near ultraviolet, mixed into the carbon dioxide haze like a ghost of alien chemistry. Normally, cyanide appears only when cometary ice begins to break apart near the sun, but 3I Atlas's release was disproportionate. It wasn't melting, it was venting from within, almost like a delayed exhalation. Across the Pacific, NASA's solar orbiter captured the object from a different angle. The high-resolution imagery showed the coma's shape warping, its inner region twisting as if sculpted by invisible pressure waves. Then, over just a few hours, the brightness curve dropped catastrophically. 3I Atlas dimmed by nearly 60%, too quickly for a smooth fade, too slowly for an impact. Theories fractured again. Some argued it was disintegration, a shattering cascade similar to Borisov's final days. Others claimed that what we were seeing was not destruction, but transformation, a volatile skin peeling away to reveal a denser, darker nucleus beneath. If that were true, it could mean 3I Atlas carried a structure designed to survive repeated star encounters, implying its journey through the galaxy wasn't a single passage, but a cycle. NASA's silence, at that point, was no longer strategic, it was defensive. Every instrument team knew what they had, but no one wanted to interpret it first. The memory of the media frenzy around Oumuamua lingered like a scar, yet the data couldn't be contained forever. A few hours after perihelion, the Solar Dynamics Observatory captured a glint, a brief, pure reflection at 1.4 AU that no dust plume could explain. It lasted only seconds, but the timestamp matched exactly with a rotational phase predicted days earlier by the leaked memo. That flash reignited everything. Could a natural object reflect light with such precision, at such distance? Was it coincidence, geometry, or something deeper in its composition? Some interstellar alloy of carbon and ice that behaved like an adaptive mirror? When the data reached ground stations, one line in NASA's encrypted summary stood out. Surface phase response exceeds expected thresholds. Further analysis required. No public statement followed. Just silence again. A silence that now felt less like caution and more like awe. In the days following perihelion, the silence thickened into something almost ritualistic. NASA's public feeds focused on routine solar monitoring, never once acknowledging the interstellar visitor that had just passed within astronomical reach. But astronomers everywhere were still awake, still comparing notes in encrypted threads and midnight calls, piecing together the aftermath from the scattered fragments of light. By November 2nd, telescopes in both hemispheres confirmed the same unsettling truth. 3I Atlas was fading, but not evenly. Its residual brightness curve fractured into two distinct sources, separated by a distance too small for resolution, but too persistent for noise. It had split. The object that entered perihelion hole was now two, maybe three irregular shards coasting outward at slightly diverging angles, and each fragment was still releasing CO2. That was the part no one expected. Usually a comet's break marks the end of its story. Outgassing stops, material disperses, and the core goes dark. But not here. Whatever remained of 3I Atlas kept breathing, still exhaling faint carbon dioxide signatures even as it receded from sunlight. JWST's infrared detectors caught those plumes at nearly 1.6 AU, weak but measurable. The fragments weren't cooling properly. Something inside them was maintaining temperature far beyond prediction. When that data reached NASA's analysis hub in Maryland, the response was immediate. Non-equilibrium thermal retention. The phrase, sterile on paper, hid an extraordinary meaning. The fragments were holding heat from within, radiating energy in patterns no other comet had ever shown. Scientists began running comparative simulations. Could electrostatic friction during fragmentation cause prolonged heating? Could trapped gases create an internal greenhouse effect? The results failed to match. The heat decay was too slow. And that raised an unspoken fear, that 3I Atlas's material wasn't inert, that interstellar chemistry might behave like an active process, not a passive one, a matter that reacts instead of merely existing. The idea was radical, yet increasingly impossible to ignore. If confirmed, it would redefine what interstellar object means, not a fossil of another system, but a remnant of dynamic matter, capable of transforming itself under stellar influence. NASA's Internal Review Board reportedly met twice that week. No minutes were made public. One rumor claimed a senior spectroscopist compared the CO2 persistence curve to a system with feedback. No one outside the circle knew what that meant or dared to interpret it. Because if 3I Atlas's fragments really were maintaining energy autonomously, if its reactions were self-sustaining, then this wasn't merely a comet from another star. It was a glimpse of interstellar chemistry behaving like a memory, something that remembers light. And just as that realization began to take hold, one of the fragments vanished from view. The fragment's disappearance shook everyone. It wasn't just a loss of visibility. It was as if one of the signatures in the telemetry simply dissolved, erased from the cosmic map. No debris cloud, no thermal residue, nothing. The smaller piece of 3I Atlas had ceased to reflect or emit in any detectable wavelength. To the teams tracking it across Mauna Kea, it was as though it had been absorbed into the black itself. The main fragment, however, lingered. Dimmer now, but still pulsing faintly with intermittent carbon dioxide traces. For the first time, NASA quietly re-entered the conversation. Through indirect channels, they confirmed what independent observatories had already begun to suspect. The remaining body was rotating unpredictably, its spin accelerating as its mass decreased. That meant it was still losing material, but not randomly. The outgassing was directional, almost precise, creating subtle thrusts that altered its trajectory beyond what solar radiation could explain. When plotted, those trajectory adjustments formed an oddly rhythmic curve, not a straight acceleration like Oumuamua's, but a repeating modulation, as if the object's surface was venting in timed intervals. NASA's public silence, in that moment, made perfect sense. No agency wanted to speculate about rhythm in an object that shouldn't have any. The astrophysical models scrambled to interpret the data. Some argued that rotation-induced fractures were opening and closing like valves, creating controlled bursts. Others pushed a different idea, that sublimation in certain crystalline CO2 layers could synchronize through internal stress waves, creating a self-organizing system. If that theory held, it would mean 3I Atlas wasn't just reacting to the sun. It was coordinating its own structural release. That interpretation frightened even the most skeptical scientists, because it implied purpose, not intelligence, but behavior. A natural object capable of pattern formation, responding dynamically to energy inputs. A molecular echo of order emerging from chaos. In an emergency meeting, the International Astronomical Union proposed reclassifying it as an interstellar volatile aggregate, a term vague enough to avoid controversy, yet acknowledging it wasn't behaving like any known comet. The motion passed quietly. Weeks later, the last confirmed sighting came from the Subaru telescope. Two faint asymmetric points drifting outward toward the dark, their combined albedo still higher than models predicted. Then, once again, the feed went silent. NASA's final internal notation about 3I Atlas, leaked days later, contained only 5 words: residual activity, unknown sustaining mechanism. And for many of us who had followed every flicker, every data drop, those words carried an unease that went beyond science. Because something out there, something older than our sun, had just reminded us that even in the emptiness between stars, matter still moves with memory. Now, as I look back at those months, the discovery, the silence, the slow unraveling of certainty, I realized that 3I Atlas was never just an object. It was a mirror, reflecting our own struggle to understand the unknown without succumbing to fear. Every time NASA withheld a statement, the world filled the void with imagination. Yet, beneath that quiet, thousands of eyes kept watching, and what they found reshaped our very definition of life and motion in the cosmos. The fragments of 3I Atlas are gone now, swallowed by distance and darkness, but their echo persists in data streams that still defy full explanation. The sustained CO2 emissions, the negative polarization, the vanishing fragment, all of it remains as unresolved signatures, pieces of an equation we're not yet ready to solve. Maybe NASA's silence wasn't about secrecy. Maybe it was humility, a recognition that some discoveries demand contemplation before declaration. Because if 3I Atlas truly retained energy beyond physics as we know it, if it responded to light in ways no inert rock should, then it forces us to confront a larger question. How much of the universe's behavior is weirder than our language can express? Perhaps silence was the only honest response. And so, we're left with a cosmic whisper, a third interstellar visitor that didn't roar through our system but lingered, exhaling its secrets one molecule at a time. Do you think NASA's silence was caution or something deeper? Tell me below.